So far in this course, we've studied matrix transformations from several different perspectives. We've looked at invertibility, determinants, bases, coordinate systems. What we're going to be looking at in this chapter and in this section is one of the most important topics in linear algebra, namely eigenvalues and eigenvectors. And to motivate that, we want to consider an example here of a matrix transformation. So we've got the matrix A is 1, 2, 2, 1. It's a 2 by 2 matrix. And we want to consider sort of what is it doing geometrically. So you could see the image below is what the matrix A would be doing to the unit square. So this is the same kind of image we've seen before. And so, in particular, we want to be reminded that sort of the first column of this matrix is going to tell us how the vector E1, which is 1, 0, gets transformed. So that's going to go to the vector 1, 2. So if we kind of drew that on here, so 1, 2 is just like that. So this is AE1, if we want to kind of label this. And then E2 goes to the vector 2, 1. So that's going to be over here, 2, 1, right? So this is AE2, okay? So we can, certainly see that something interesting is happening here, and we could compute the determinant of this. We would find that it was, I guess, -3. So that's the area. The area of this particular object is 3, and the negative sign tells us that there's some sort of a flipping or reflecting going on. And there's a stretching going on, right? Because we have that 3 value in there, but sort of exactly what's happening is a little bit hard to tell. Is there rotating? Is there stretching, reflecting? Is there a combination of these things? And sort of how exactly do these all play together? So that's something that our study of eigenvalues and eigenvectors is going to help us determine. So instead of studying what A does to every vector, what we do to begin here is look for vectors whose direction either does not change or sort of changes to the exact opposite direction. So we are in particular looking for a vector V such that AV either points in the same direction or in the exact opposite direction as V. And this in general is maybe a pretty challenging question. We could play around with different vectors and see sort of what happens. What I'd like to do is actually switch over here to our book, which includes this really nice applet in the section that allows us to input a particular matrix, as long as the values are between -2 and 2. So let's put our matrix in 1, 2, 2, 1. So 1, 2. We're going to do these sliders here, and then 2, 1. And what you could see down here is a vector in red and then a vector in white. And what this is basically doing is showing you, as you change that red vector, how it gets transformed under this particular matrix. So the vector 1, 0 goes to 2, 1. We already saw that, right? So that was, or excuse me, 1, 2. If we go to E2, that goes to 2, 1, so we could see those two. But what this also allows us to do is sort of play around with this. And again, our goal is to find a vector such that, when we transform it, we end up with just a vector that points in the same direction or, again, that exact opposite direction. And so, as you're sort of spinning this around, you might land on something. And you can see right here, it looks like if I input the vector 1, 1, for example, then it almost perfectly transforms to the vector 3, 3. So it seems like 1, 1 is sort of a special vector here. And then again, I can kind of keep spinning around and we could see maybe the vector -1, 1 kind of perfectly points in the exact opposite direction to the vector 1, -1, right? And we're not going to get other vectors except for sort of pointing in the exact opposite direction of those ones that we just picked that do this. So those seem to be sort of these special vectors. So what did we kind of just discover for this particular matrix? those vectors, again, 1, 1 and negative 1, 1, seem to be sort of special. If we were to consider A times V1 doing our matrix vector multiplication, we would get, I guess, 1 plus 2, so 3, and 2 plus 1, so 3. And notice that this is exactly 3 times V1. So when we transform that vector 1, 1, we end up with a vector that scales it by 3 and moves in the exact same direction as it. If we looked at A V2, then we'd get, again, doing this vector matrix multiplication. I guess that's negative 1 plus 2, so that's 1, and negative 2 plus 1, so negative 1. And notice that is negative 1 times our original vector, or negative v2. So we end up with a vector that points in the exact opposite direction as our original vector. Okay, and so this sort of demonstrates that geometrically. We could see that AV1 is going to end up being just pointing in the same direction as V1, but be exactly 3 times as long as it, right? And so if we kind of, there's V1, and then again AV1 drawn on there, same direction, 3 times as long, V2, and then AV2 sort of pointing in the exact opposite direction as it. Again, what we demonstrated algebraically a few minutes ago, that AV1 equals 3V1, AV2 equals negative V2. So the vector V1 is stretched by a factor of 3. The vector V2 is reflected and scaled by a factor of 1 or negative 1, I guess actually would be maybe a better way to say that. But the reflected idea is, I guess, getting at the fact that that is a negative 1. If we consider the vector, or excuse me, the matrix D, which is 3, 0, 0, negative 1, so this is going to be a matrix, and if we think about this matrix transformation, it's going to take E1 and move it to 3, 0. So 1, 0 moves to 3, 0. And it's going to take E2 and move it to 0, negative 1, right? So 0, negative 1, much easier to see exactly what's going on here. This is taking that unit square, it's stretching it horizontally by 3 and reflecting it by, over that x-axis, or E1, E1 axis, I guess, sort of reflecting it vertically. Not as much mystery as our original matrix, but sort of in a way, sort of doing the same thing as our original matrix. So kind of what's coming here, if we think of these vectors, so v1 is 1, 1, v2 is negative 1, 1, these form a basis for R2, because they are going to span R2 and they're linearly independent. You can sort of check that or go back to some of the sections we were talking about bases. So relative to this basis, the matrix A that we've been working with behaves sort of like the matrix D if we consider our kind of standard E1, E2 basis for R2. So we've sort of changed our basis to V1 and V2, but in a sense, we have kind of this simpler matrix D. This is a diagonal matrix, and in some ways, A is equivalent to this diagonal matrix D if we are sort of viewing it under the right light with the right basis. So this is something that we're going to make more precise as we move through the chapter, but I thought, kind of starting with this geometric motivation for eigenvalues and eigenvectors would be nice. We're going to get into all the nitty gritty of how to compute these things, and the some of the uses of them. Why do we even care to have this diagonal matrix? Beyond just sort of the fact that it allows us to view it in a bit of a simpler way and see that geometry. So we're going to get into all that in this chapter, but hopefully this gave us a good bit of motivation for at least sort of the geometry of these things.